So today's topic is matrix chain multiplication, and we will discuss that what the problem of matrix chain multiplication applies and how we are going to solve this. So matrix chain multiplication problem is that we have been given a chain of matrices, and every matrix A1, A2, AN, they are having their dimensions. Now the problem is that we need to determine the order of multiplication or the way of parenthesizing the product of matrices so that the number of required operations can be minimized. The concept here behind this matrix chain multiplication problem is that, for example, we have been given 4 matrices. So my 4 matrices are A1, A2, A3 and A4. Now, for example, if I want to compute the product of these 4 matrices, I need to think out on a way as where to start from. So for example, for the same given sequence of matrices, I can parenthesize, or I can compute the product in these different ways. Now, why there are so many different ways to multiply these matrices? So we all know that matrix multiplication is a binary operation, and to perform the matrix multiplication or to find out the product, we first need to pick up 2 matrices which are multiplication consistent, and then we need to perform the product, or we need to calculate the product of these 2 matrices. Then whatever product we are going to have, that product we are going to multiply it with another matrix, and that way we are finding out the multiplication of the product of n number of matrices. So in this case, what we can see that, for example, if these are my matrices, so I have A1, A2, for example, A3 and A4. Now, for example, first of all, I pick up these 2 matrices for multiplication, right? And we need to keep in mind that the matrix which we are picking up, they need to be picked up in the same order. Okay, so we can insert the parentheses around this expression, but the sequence of these matrices need not change. Otherwise, they may not be compatible for calculating the product. So for example, if I first pick up A1 and A2 and I try to multiply these 2, I am going to get one product out of this multiplication. For example, this multiplication product is denoted as P1. Now, to do further multiplication, I need to multiply P1 with A3. So in this way, I am getting another product, for example, which is called as P2. Now, this product needs to be multiplied with this, and again, I'm going to get another product which is called as P3. And this P3 product is the solution for this chain of matrices when they are going to be multiplied together, right? Now, how I am going to pick up 2 matrices to multiply first, and after that, that decides on the order of parenthesizing this expression or this chain of matrices. So in this case, for example, the first expression says that we are first picking up these 2 matrices together, then whatever product is generated, we are going to multiply it with another matrix, and then we are going to multiply the product of this with A1. So this is my sequence of performing the same matrix multiplication. In another way out, what I can do, that I can first pick up A2 and A3 and just try to multiply them. Once I multiply, I will get some product, and that product I'm going to multiply with A4. Now again, I will get the product of multiplying A2, A3, A4, and this product I'm again going to multiply with my matrix A1, which is left for calculating the product. So again, this is another sequence of putting parentheses around this chain of matrices. In another sequence, I can first multiply A2 and A3, and then rather than going to A4, I can use this product and multiply it with A1 first, and then whatever product is going to be generated, that product I'm going to multiply with A4. So again, this is the same way of accomplishing matrix multiplication of these chain of matrices. In another sequence, I can first multiply A1, A2 together, then product of this is going to be multiplied with matrix A3, and then the product generated from here will be multiplied by A4. So this is another sequence. The final sequence is that I can pick up A1, A2 first, then I can pick up A3, A4 first. I'm going to get up two different products, and those products I'm going to multiply, and I will get the product of this chain of multiplication. So as we can see here, that for a given chain of matrices, how we are going to multiply, or how I'm going to select two matrices at a time to perform the multiplication, that can be done in a variety of ways. Now, why this problem is important? So let's see that why we are interested in finding out in which way we need to multiply the matrices together. Is it going to make some difference, or what is the underlying idea behind observing all those parenthesizing expressions, that where to put parentheses and where to not? Okay, so this we will see with the help of an example. So as you can see, for example, the four matrices we have picked up are each having these dimensions. So for example, A1 is of dimension 10 cross 20, A2 is of dimension 20 cross 50, then A3 is of dimension 50 cross 1, and A4 is of dimension 1 cross 100. As you can see, the chain of these matrices, since the inner dimensions are matching, so they are perfect for multiplication, right? So I have put up or taken up this sequence here, A1, A2, A3, A4, and I have written down the dimension of these matrices here. Now, for example, if I parenthesize this chain of matrices in this way, so how many total scalar multiplication I am going to perform, that I need to find out here. Okay, so for example, the first way out in which I am putting a parenthesis around A3, A4. So this denotes that first I have picked up A3 and A4 to multiply together. So now as you can see, if I do this here, I'm trying to calculate A3 multiplied by A4, right? What are the dimension of these two? So A3 is 50 cross 1 and A4 is 1 cross 100. We are not repeating the inner dimension. So when we are doing the product, if you remember that when two matrices are multiplied, the total number of multiplication that we are going to perform will be equal to now 50 cross 1 cross 100. Okay, so if I try to multiply these two matrices together, the total number of scalar multiplications that I need to perform, those will be around 50 cross 1 cross 100. And if I evaluate, this will come to 5,000, right? So 5,000 multiplication operations I need to perform here, and the product dimension out of this multiplication, that will come to 50 cross 100. Okay, so for example, when I'm multiplying A3 with A4, the product that I'm going to have is named as P1. So this P1 matrix, or the result matrix of this multiplication or this product, is actually having the dimension of 50 cross 100, right? Now, the next sequence that we have picked up here is that whatever product, I'm denoting this product as P1 here. Now, whatever product I have calculated in this, that product is going to next multiplied by with A2. Okay, so now I'm trying to multiply P1 with A2. The dimension of A2 is 20 cross 50, and dimension of P1 is 50 cross 100. So as you can see, the inner dimensions, they are matching, so these two matrices can be multiplied together. And now how many computations, or how many scalar multiplications I need to compute? So for example, in this case, when I'm doing A2 multiplied by P1, I'm going to perform 20 cross 50 cross 100 scalar multiplications. If I calculate this and make a total here, for example. So this will come to, for example, okay, so these many, multiplications I need to calculate. Now, whatever product is going to be generated from here, so when you multiply these two, again a product will come, which is called as P2, okay, and this P2 will have a dimension of 20 cross 100, right? Now I need to multiply this product P2, right, with A1. So I will now write A1 here, and I'm trying to multiply A1 with P2. A1 is having dimension 10 cross 20. Again, the inner dimensions, they are matching. So we know that these two are conforming for the product or for the multiplication. And now in this case, again, I'm going to calculate the total number of multiplication operations, scalar multiplications that I need to perform. So the total number of multiplications will be 10, 20 cross 100. Okay, if I multiply these two, this will come to 20,000 multiplications, right? Again, I will get a final product, which I can denote as P3, for example. And since I am not left with any of the matrices here, so this is my final product with dimension 10 cross 100, right? But to find out this product, how many total scalar multiplications I have performed. So I have performed these, and these many operations. If I add up all these operations together, then this will be, for example, this, then I have 5,000. If you add up them together, then you will get 0, 0, 0. You have 5, 2. So you have 12, you have around, these many number of matrix multiplications or scalar multiplication that you have performed. Now, if I change the sequence of these matrices, for example, and I try to multiply A2 by A3. So first, if you take A2 and A3, right? Now the total number of multiplication that I need to calculate here will be equal to 20 cross 50 cross 1. 20 cross 50 cross 1. And this will give me 1000, scalar multiplications. Plus, when this product comes, I need to, calculate or multiply it first with A4. So now the product here will be of dimension how many? So this P1 now going to have a dimension of 20 cross 1, right? And I'm multiplying it with A4, right? A4 is having dimension 1 cross 100. So how many computations I'm going to perform now? These will be equal to 20 cross 1 cross 100. Okay. If I calculate, it will come to 2000. So previously I have calculated, 1000 products, and now I have calculated 2000 more products. And again, since the multiplication is not completed right now, whatever product has been generated after this needs to be multiplied with A1. So now the product of this operation, which is, for example, P2, and this P2 is having a dimension of, there will be 20 cross 100. Okay, so this P2 now is going to be multiplied with A1. A1 is going to have dimension 10 cross 20. Okay, so inner dimension is again matching. So 10, 20, 100. Okay, this will be the total number of calculations that I need to again perform. This will come to 2, 1, 2, 3, and 4. So 20,000 calculations I need to perform. If I add up all these three together, so I will have 2000, then 1000, and this will come to 23,000. Okay, so in this case, now I'm only performing 23,000 multiplications. And if I see the previous sequence, I have performed how many? 1 lakh 25,000 scalar multiplications. So you can see there is a huge difference between this and this figure, and here the number of scalar multiplication that I need to perform to multiply the same chain of matrices is coming to over 1 lakh operations or multiplication operations, and here it is reduced to 23,000, right? So there is a significant difference here. So this example actually tells us that if we find out the optimized way in which we can parenthesize the expression correctly, then the number of scalar multiplications that we need to perform to multiply a chain of or a sequence of matrices, that can be reduced or that can be computed faster. Okay, so we are interested in finding out an algorithm that gives us the efficient sequence of these parentheses around the chain of matrices, so that the total number of matrix products or scalar products that I'm going to calculate will be lesser or will be minimum. Okay, so there are multiple ways. Again, I have not explored each and every every sequence. So as an exercise, you can calculate how many scalar multiplication I need to be calculating for if I put the parentheses in this order. So for example, if I first compute A2 multiplied by A3, and then I will multiply the product with A1, and whatever product has been generated, I multiply it again with A4, right? So how many operations or multiplication needs to be done. So this is the problem of matrix chain multiplication. And as you can see here, that when we are multiplying the matrices, the matrix multiplication takes a lot of time. So if we are doing the multiplication of matrices even with a computerized algorithm, right, it is going to take up a lot of time. So in normal cases, if we are using a normal matrix multiplication method, okay, if we try to multiply two matrices together, which are square matrices with dimension n cross n, then in that case I need to calculate these many products. Okay, so the scalar products will be equal to n cube, right? N is the dimension. Or I can say that the algorithm that computes two matrix that computes the multiplication of two matrices is going to have the complexity or the time complexity of order of n cube, right? If we use the Strasson's method to improve over this time complexity, even then for multiplying two square matrices together, the time complexity comes to order of n raised to the power 2.8 something, right? Which is again very high. So if my problem involves a lot of matrices and I need to multiply them together, as the number of matrices is increasing, the algorithm time is going to be increased, and I need to find out an efficient way how I can minimize that time. And for that, we already have seen that if we can find out how we can parenthesize this expression efficiently or an optimized way, the total number of products that are going to be calculated can be reduced. Okay, so matrix multiplication or matrix chain multiplication actually is the problem that we have discussed today. How this problem is going to be solved up? So we have dynamic programming approach through which we can efficiently find out the solution of parenthesizing the sequence of matrices, and to find out that which matrices needs to be multiplied first and afterwards. So we will see in the next lecture that how the dynamic programming approach can be applied to this problem to find out the solution of this problem. Thank you very much.